Hey everyone, thank you for attending my presentation today. My name is Tahniat Afzari. I am first year doctoral student, Nanoscience Department from UNCG's Joint School of Nanoscience and Nanoengineering. I am studying nanorobots' controllable motion, their collective behaviors and mechanism. And my presentation today is nanoscale rotating robots offer new promising biomedicinal applications. Nowadays, motors are a part of everyday life and deeply ingrained in almost every aspect of technology. Similarly, every living cells and organism's vital components are microscopic biological motors and machines. Collectively, it can call as nanorobots. Representative illustration of synthetic and biological motors on different length scale is shown in this picture. The natural motors listed on the top of the row are kinesin at a nanometer length scale, a swarm of E. coli bacteria at a micrometer length scale, and a ladybug at a few millimeter, and a Vitruvian man by Vinci, which is 2 meter in length scale. At a similar size, synthetic motors illustrated on the bottom row are nanocars, micromotors, fabricated robotic insects. These fabricated nanorobots convert energy from surrounding to motion, which is similar to microorganisms' motion. Functional robots on the nanometer length scale is challenging. Not only it is difficult to fabricate complex objects of nano size, but because of powering them. As an example, nanocar in this picture has wheel to roll on the surface, but no internal power to make them go. Synthetic robots that are powered by self-generated gradients have been the subject of growing interest and studied since their discovery in 2004. To understand nanorobots' motion, we have to consider their size because at macro scale they can maintain their motion with inertia, but at nanoscale objects have decreased inertia that is near to zero at low Reynolds number. Nanoscale objects have Reynolds number as same as that moving bacteria. The top figure shows the schooling behavior of biological organisms, and the bottom picture shows the same schooling behaviors of nanoparticles under ultraviolet light. Nanorobots that function in aqueous media experience collision with water molecule, become significant as their size decreases. Brownian motion introduced by such collision becomes significantly interferes the direction of motions and appears to diffuse randomly. Tiny nanorobots face challenges at low Reynolds number to get effective motion. To maintain motion at low Reynolds number, a constant instantaneous force is needed to induce instant motion. That can be chemical, acoustic, magnetic, or electrical. The second challenge is to design robots that movement is non-reciprocal. To induce motion at low Reynolds number, symmetry needs to be broken. It can be time reversal symmetry or symmetry in particle compositions, shape, and surface reaction. Autonomous nanorobots can be divided into three main categories: motors, rotors, and pumps that are designed to break symmetry and induce motion. Nanorobots under external power interacts with each other, exhibits potentially useful emergent collective behavior. Under chemical power, autonomous motors show chemotaxis, predator prey, schooling, and exclusion. The study of how these synthetic nanoparticles interact with each other may lead to better understanding of how cells and bacteria communicate with each other. Variety of factors, both external and internal, can affect nanorobots' behavior. These include fluid viscosity, permeability, fluid concentration, and their size and shape. An additional evaporated layer also introduces a rotary motion by breaking down their symmetry. Self-electrophoresis is a dominant mechanism for catalytic motors in liquid medium. Charged particles move in a self-generated electric field as a result of asymmetric distribution of ion. In bimetallic nanorod, oxidation of hydrogen peroxide preferentially occurs at anode and reduction in cathode end. This bipolar electrochemical reduction generates high concentration of proton at anode and low concentration of proton at cathode end. Since the protons are positively charged, the asymmetric distribution results in electric field pointing from anode to cathode. The negatively charged nanorod therefore move in the electric field. The serious drawback of chemical propulsion is their reliance on toxic fuels, such as hydrogen peroxide. For this, there is a need of new propulsion mechanism that can generate autonomous motion also in biological media. Acoustic power is promising for propelling nanorobots. In an acoustic field, particles experience acoustic radiation force and move to the pressure node as a result of pressure gradients. At constant standing wave, nanorods levitate on the midplane of the acoustic chamber. At that midpoint, they experience autonomous motion and interact with each other. In our project, we are studying collective behaviors of large number of nanorobots, motion and interactions. We are observing nanorobots' behavior under acoustic power and studying their collective behavior under combination of acoustic and chemical chamber. The works being done in Ahmed's lab include electrodeposition, evaporation, and ACM. We are designing nanorods and use them to study large-scale nanorobots' collective behaviors and their interaction mechanisms in acoustic and also in dual power. This offers a new possibility of controlled functionality that can be applied for future vitro and vivo applications. Nanorobots' controllable motion will allow us to precisely use them in sensing, drug delivery, tissue drilling, and tumor cell detection. I want to thank you everyone for attending my presentation. Hope you enjoy it.